I'd like to introduce Jon Oxer, who's going to do our presentation this afternoon, and I think everybody's interested in shooting stuff at the moon, so this should be great. Jon.
Here at LCA in Hobart, Marco Ostini, who is just down the front here, did a lightning talk asking for people who are interested in getting involved in a team going after the Google Lunar X PRIZE. And I was really surprised because I thought he was going to be, beaten to a pulp in the stampede of people wanting to help. And he wasn't. In the end, there were 4 of us. So there was Marco, obviously, Andy Gelmy, Lee Begg, and myself, who formed Lunar Numbat. And I thought that there would be a whole lot more people wanting to help out. I mean, everybody loves rockets, right? How many people went to Bidal's talk yesterday about rockets? Yeah. That was really cool. So Lunar Numbat, as I mentioned before, is a group of 4 people so far, plus a whole bunch of others who are interested in following what we're doing, but not necessarily getting involved on a regular basis, who are working with White Label Space to provide some of the little bits of technology that could be of interest to them. Now, one of the drivers for White Label Space, as I said earlier, is they want to not simply buy a whole bunch of off-the-shelf pieces, bolt them together, and come up with a mission. They really want to try to come up with some little new elements along the way. And this is where Lunar Numbat comes in. White Label Space has a particular interest in open source in terms of trying to not just achieve the end result, but achieve it in a way that new technology is developed, people are able to become involved, and that technology becomes useful for other people. The idea is to lower the barrier to entry to space technology for everyone, not just to pull off some one-off mission and then have nothing happen after that. Okay, so before you were born, the Russians put a couple of these on the moon. This is Lunokhod 1, which went up in November 1970, drove around on the lunar surface for 322 Earth days, traveled 10.5 kilometers, and sent back photos like this one. This was a photo looking back at the landing craft after it had driven off. And Lunokhod 2, which went up in 1973, lasted, I think, 4 months, and it drove 37 kilometers. And this was 40 years ago. And it seems that not a lot that's been really exciting has happened since then. Now, of course, we've got the shuttle program, we've got all sorts of other things, but it still kind of feels incremental. And it feels very inaccessible. It feels like we can't really get involved with it. These are mega-scale projects that individual open source people can't really do much with. So, basically, I've been asking myself the question, what's stopping us? Why don't we have moon bases? Why can't I go to What If and find specials on, Tranquility Base, spare rooms, or something like that? We should be able to do that by now. In December, the White Label Space team put out their preliminary mission concept, and this outlines the sequence of events, how they want to run their mission. So basically what I'm going to do is take you through the steps of what's going to happen over the next couple of years. Well, this is the outcome of the mission. And point out some of the ways that you can actually get involved. So the first stage, obviously, you've got to get out of Earth's gravity well, and that takes some pretty serious hardware. So this is a PSLV XL lift vehicle, which is an Indian vehicle which has just ended operation in the last couple of years. And the proposed mission profile involves lifting into a geostationary transfer orbit using a PSLV XL. Now, this thing is a pretty serious piece of hardware. It's rather large. To put it into perspective, so here's me in one of these little Class C rockets. Change the scale a bit. That's one of these lift vehicles. That's 44 meters high, weighs 320 tons at takeoff, and it can throw a couple of tons into Earth orbit. And so there are a couple of options here. At the moment, the PSLV XL is the preferred lift platform, but there is also an option to use a Falcon 9, which is another even heavier lifter currently under development by SpaceX in Texas. And what you see in that particular picture is the trajectory of a direct moon intercept course. So the Falcon is a much bigger machine, and it can lift. It can actually go straight into a lunar injection profile. So the way it would be done with the PSLV would be to use the PSLV to get into orbit, and then there is a Star 30 BP, which is a massive rocket engine strapped to the side of the payload or under the payload. And it then does the transfer from geostationary transfer orbit into a translunar injection phase, which is when it moves out of Earth orbit and heads off towards the moon. Now, there are two different ways the payload could be configured. The one on the left is using the PSLV, which is the preferred method, and this is a dedicated payload. So what you can see in the stack there is the little rover sitting right up the top, the tiny little thing. There is a landing craft. Below that is a big grey rocket motor. That's a Star 30 BP, which is the braking engine. Below that is another Star 30 BP, which is for the translunar injection phase. The other nose cone you see there, which the scale is not the same. The one on the right is actually quite a bit bigger. That's the nose cone of a Falcon 9. And this is the stack as it would be used using the PSLV. Okay, so what we're looking at here is a lot of very serious hardware, very serious money. And you're probably thinking, what can we do? How do you get involved in this sort of thing? This is really just a case of take a few tens of millions of dollars and throw it at a problem, and it gets fixed. And there's not really all that much scope up to this stage of the project for open source hackers or random individuals to get involved. But there are lots of really interesting things that come on after this point. It's really once you get into lunar orbit and then on approach for landing where we can start contributing. So this is the stack as it would be approaching the moon. Doesn't matter which profile is chosen. The end result is going to be a stack like this approaching the moon with the braking stage at the bottom, which would then separate, and the orange lander, which is what actually comes down and touches down on the moon's surface. There are a couple of interesting aspects to this. Firstly, one of the things that we've been contributing to a little bit is the altimeter. There are all sorts of interesting technical problems, and this is the whole point of this talk. There's lots of stuff here that there are problems waiting to be solved. One obvious one is, how do you tell how high you are when you're trying to land on the moon? There's no GPS constellation. You can't measure air pressure. So really the only feasible way to do it is some kind of a reflection system. And so Lee has been working on a radar altimeter, which basically is like echolocation. Sends a signal down, bounces back, and you see how long it takes. And there's some really interesting work being done on that. So if there are people that are into RF and like playing around with some really interesting things, and he's also been investigating the possibility of doing this using software-defined radio. Lots of interesting software problems in there to be solved if you're that way inclined. So I'm sure Lee would love some help in that sort of area. Other stuff we've been doing is the throttle control. As the lander comes down, it's going to have obviously a big rocket engine which is going to control its descent rate. And we need to be able to continuously vary the throttle. Now, one thing you may not know is that a lot of landers that have been used in the past are actually extremely low tech. They're far more crude than you might imagine. Like, we've got this concept that they're super high tech, everything is really well tuned, and they're remarkably not. There are a few of the landers, for example. There was one I saw some specs on just recently. They wanted to vary, I think this was one of the Mars landers, they wanted to vary the thrust as it was coming into land. And they couldn't vary the thrust on the engines. All they could do was turn them on and off. So they stuck 16 engines on it, 4 on each side, and they just pulse width modulate them. So as the thing's coming down, the engines are turning on and off very fast, and it's shaking like crazy. And it worked, but obviously it's a bit of a brute force solution. It's fairly crude. And so we've been working with ASRI, actually, which is the Australian Space Research Institute, on their OSROC program. The next major rocket design that they're working on is OSROC 2.5. And that's what this throttle body is from. What you can see here, up in this section here, the propellant basically flows through here. This is a liquid oxygen kerosene-based propellant. And inside there is a ball joint throttle valve, which is continuously adjustable. So we've been playing around with control systems for how to control the position of the throttle, get feedback on current throttle position and stuff like that.